Hello, good morning, good afternoon, good evening. Thank you all for joining us for the eighth and final session of the 8th Annual HOMER International Microgrid Conference. My name is Tricia Fitzpatrick. I'm the Marketing Manager for HOMER Energy by UL, and we're very glad you have joined us for our 8th year for the conference. Each year we come together to learn from experts in the field, and even though we are virtual, this year has been no different. In our previous sessions so far, we have covered many key topics. We have looked at the current and future growth of microgrids in the US and worldwide, looked at the role of microgrids for emergency response and resilience, both off-grid and on, seen work on recent advances in energy access, and discuss the status and impact of regulations, as well as the challenges and solutions for energy for islanded communities. And we have come together from all over the globe. This is our highest registration ever, and you have joined us from 136 countries. The graph on the screen shows just 21 of those, and we're very glad to have you all here. We'd like to give a big thank you to all of our sponsors and encourage everyone to visit the sponsors' virtual booths on the conference website. These leading companies have made a lot of content available on their booths. They're bringing you additional learning opportunities, including webinars, future events, one-on-one meetings, white papers, videos, and more. So be sure to visit the booths and take advantage of those opportunities. The booths are at the conference website, microgridconference.com, under the Sponsors tab. We want to especially thank our full conference platinum sponsors, Rolls-Royce, bringing you microgrids from MTU, which range from battery storage to fully integrated hybrid systems. Rolls-Royce is focused on providing cost-efficient microgrid solutions that support smart functionalities. And platinum sponsor ETAP Microgrid Control Solution, which offers an integrated model-driven cross-platform microgrid controller to facilitate optimal and reliable control of microgrids. The solution enables you to seamlessly operate and transition between grid-connected and islanded modes. And our final session today is Controls, the Key to Sustainable Microgrids. It is one of our most popular sessions, so we have a very full house who have joined us for a packed agenda with a strong lineup of presenters. Today's session is brought to you by the newly merged wind energy companies of EOCycle and Zant. These companies are bringing you wind power made easy for on-grid or off-grid applications with or without storage. And now for those of you who are joining us for the first time, let's talk about how to ask questions. This is one of the best parts of our conference, and so we are using the Slido app. In Slido, you can enter your questions and also upvote other attendees' questions. It's easy to log on from your phone or computer. If you want to use your phone, you can take a picture of the QR code on the screen, and your QR reader will take you right there. Or you can simply open a browser window on your computer or phone, and in the search bar, type in slido.com, and then when you then in the Slido window, you can type in HIMC 2020, which is the conference code. That's HIMC 2020. And now you can type in your questions as you think of them. Since we have a number of speakers, if your question is for a specific person, you can write that in your questions, and then you can upvote the questions you most want answered, and they will rise to the top. And we will get to as many questions as possible at the end of the session. So now we want to go ahead and go over to the Slido screen so that we can take a look at Slido. We are running a poll right now, which is a conference-wide poll. It's how long have you been in the microgrid and distributed energy industry? And you can see that we have quite a range of people here. We would like to know how you all fit into that scenario. So please do go and answer that poll. Of course, we have more people that are new to the industry, but we have a really big range, and we actually have quite a few people that have been in this industry for more than 10 years. So we are going to close that poll now so that we can take a look at, we have a session-specific poll. And that poll is which statement best expresses your view of the future of storage for power applications? There's quite a range of answers there that you can consider, and people are answering that. Other storage technologies not suitable for vehicles will become a major player in the power industry is taking the lead at this moment, but we'd really like to know what everybody thinks. We're going to keep that poll open until the end of the session, so you can answer it later if you prefer, and also if you change your thoughts on that, you can always go and change your answer. So now I'm going to switch the screen back, and I would like to get the presentation started and hand the mic over to HOMER Energy founder and UL Global Microgrid lead, Dr. Peter Lilienthal, to introduce our speakers. Peter?
Well, thank you, Tricia, and thank you all for joining this last session of our 8th annual HOMER International Microgrid Conference. This session is Advances in Technology, Batteries, and More. We've got 5 speakers. The first speaker is Michael Blaus, is the founder of Strathmore Energy. He studied electrical engineering at the University of Sydney and earned his MBA from the Charles Sturt University. Michael has worked in the tech industry for nearly 30 years in manufacturing, supply chain management, and transformation for IBM and Apple. During a 5-year sailing sabbatical, he discovered firsthand the needs of off-grid systems and learned about lithium and lithium titanate technology. In 2019, he developed a lithium titanate battery, the T-cell, and founded Strathmore Energy. Our second speaker is Brian Ballack, is a commercial analyst at Invinity Energy Systems. He has 15 years of experience in energy sector roles, including solar, biomass, and energy storage, with a focus on strategy, business development, and project planning. Brian holds an MBA from the London Business School and an undergraduate degree in philosophy from Willamette University. And he'll be talking about flow batteries. Duncan Campbell is Vice President of Project Analysis at Scale Microgrid Solutions, which is a vertically integrated microgrid as a service company. He's responsible for assisting the business development team in project development activities, ranging from conceptual design to dispatch optimization and financial analysis. Duncan also is a co-founder of the DER Task Force, a community of distributed energy professionals and enthusiasts that are driving this space forward through high-value events and digital media creation. Duncan received his BS in mechanical engineering from Temple University and holds professional certificates in business and financial modeling and energy innovation and emerging technologies from the Wharton School of Business and Stanford University. Peter Hussinger is a product solution development engineer at Baiwa Solar Projects. He specializes in commercial and industrial applications and has overseen pilot projects, tool development, and the modeling and evaluation of energy storage projects. He's also an assistant professor at the University of Applied Sciences in Karlsruhe and is a lecturer for renewable energy storage and energy storage lab for international students. Final speaker is Drew Lebowitz, is a senior consultant for DNVGL's energy storage engineering team and is currently on a team that designs and evaluates microgrids and storage solutions. From 2010 to 2018, he lived and worked in Latin America and the Caribbean on electrical utility projects for a wide variety of projects with private companies, governments, and international organizations. He's an expert in hybrid diesel microgrids, smart metering, solar EPC, battery safety compliance, and international utility operations with a focus on developing countries. And with that, we'll get started.
Well, good morning, everyone. Thank you, Peter. HOMER team. I'm delighted to be here to present the economics of T-cell-based microgrids at the 2020 HOMER conference virtually. Economics is about solving problems of scarcity. And we do have a new problem of scarcity in this world of abundance, and that is cheap energy. I will show you in a moment how serious that has become in Australia. But my contention is that the electricity problem now is that it's really only centralized legacy grids that were providing affordable power to consumers and businesses. And for all the effort in renewables, that still hasn't been achieved. There's a missing piece. That missing piece is my contention, can be solved with T-cell. Adding T-cell battery systems to renewable energy projects in many cases can make the third leg of affordable electrical energy, and the answer is due to the long life 20,000 charge cycles from T-cell. What is T-cell? It's a lithium titanate based lithium-ion battery. That's what gives it the 20,000 cycles. In the industrial design is a modular one, making it highly scalable. It includes an integrated BMS, can be operated as standalone to manage and keep the product safe, or it can be connected via CAN bus to communicate to downstream systems. At the moment, T-cell is built here by Strathmore Energy, a regional Australian startup. We're hoping with interest, further demand, that we can expand internationally. As we get started, what is the ideal electricity rate? Well, it's for this discussion, it's dollars per kilowatt hour, because that's what people talk about with electricity prices. You could do a simple survey, Google a simple survey, and I think you tend to gravitate towards about 15 cents a kilowatt hour. That's certainly an existing rate, a looking backwards rate on legacy centralized grids around the world. Let's have a little look. Let's have a drill down now and look at one particular case study, which is the Australian rates, the ones I'm recently the most familiar with, although I am familiar with others. There's a couple of key points that jump out at a track of Australian electricity rates. It broke back in 2010. Prior to that, Australia had very good legacy grid rates, and they tracked the general rate of inflation over a long time interval. You can see there in 2010 they broke away. Instead of about 2% yearly increase in price, they pivoted to about 8% on a fairly linear basis, to the point now that electricity prices in Australia average around about US 25 cents a kilowatt hour, way too high, and worse, inflating well above the average. Another key point to take away from this chart is that electricity would have been USD 13 cents a kilowatt hour if it had continued, it had not broken away in 2010. So it really was a very pivotal point in the history of Australian electricity, 2010. We could talk another day about what happened outside of the business of electricity, but affecting it nonetheless because it's a capital-intensive area. The cost of money, and all capital projects are highly dependent on the cost of money. Another very interesting and important phenomenon has occurred, and that is the continual decline of interest rates over the same time period. So much so now that nominal rates are bouncing around at zero, meaning that real rates, and particularly real energy rates, are highly negative. This has a very profound impact on business decisions when it comes to capital plans, and I'll show you in a moment exactly what that translates to. Going forward, for most projects, I'm using a very low discount rate for energy-related projects, essentially because they're very low risk. Very low risk in an environment where the weighted average cost of capital is so low. You should be using a low discount rate. Combine these two things, breakaway electricity, legacy grid electricity rate, and a plummeting, inverting interest rate, and you start to see the situation that's happening with electricity. Let's look at that 2010 quickly. The nominal rate was 14 cents. We had a discount or background inflation rate of 6%, and grid inflation approximated the background inflation of 2%. So for for comparative purposes, I look at what a forward rate. What was a forward? What was the situation looking forward with electricity rate? So you can do a net present value on the electricity rate. So with those parameters, the forward electricity rate, as viewed in 2010, was 9 cents a kilowatt hour. And typical exchange rates today, that's about 6 US cents. Very, very benign. But look at that electricity inflation rate the last 10 years. Look at what's been happening to the cost of capital. Put those two things together. The situation changes. Here's the grid now. So we have that very high starting rate, nominal rate. We have almost zero inflation rate, and we have much, much higher grid inflation. Take the net present value of that and look what happens. The USD forward rate has jumped from 6 cents a kilowatt hour to 65 cents a kilowatt hour. That's right. In 10 years, we've seen a 10x deterioration in the cost of electricity, forward-looking cost of electricity in Australia. This is a disaster. This is an absolute cataclysm. I mean, I've never seen the destruction of a major system to this extent anywhere in the world, although I expect in some jurisdictions this is in fact what's happening. I suspect probably California and Hawaii, maybe parts of Europe have seen this. And I think there's a lot more. I think if you look at your own region where you're operating, you might be working from legacy grid systems that are approaching end of life. I suspect that grid now column is what you're about to face as people look to see how they're going to supply electricity in the future. So there have been some attempts in Australia to solve this, try and claw back some of that, that better history. And the main way that's been done is by adding solar. I think Australia now, if it doesn't have the highest, it certainly has close to the highest take-up rates of solar anywhere in the world. And this chart shows you exactly why. Now it gets a bit harder now. Those first two columns you can compute just as a simple growing annuity. But when you want to put solar into the mix and really take account of what's going on, this is where tools like HOMER really jump to the fore. You have to use them. So what people have done in Australia to sort of solve some of those terrible electricity situation rates that we have today on the grid is they've added in solar, and you can see there what it does to the forward-looking rate. So rather than 65 US cents forward rate, by adding a typical amount of solar to a typical consumption scenario, people are dropping that rate to about 22 cents forward-looking. It's not as good as what it was in 2010. It's also not as good as my ideal rate of 15 cents, but it's certainly a lot closer than 65 cents by just staying on the grid. But as you can imagine, what is that, a Newtonian physics, body in motion will continue till it meets a force in the opposite direction. We now have too much solar in Australia. So essentially, we still have the duck curve. We have all this solar typically occurring at a time when we don't need it. On the right-hand side of the chart there, you can see that we have pockets of extreme negative energy in Australia. This is where the rates for generation becomes negative, and generators have to pay to put their electricity in the grid. We've kind of reached the end point in this adding solar game. So again, if you flip back to this chart and start to contemplate what's going to happen into the future, the economics are not looking too good. We're going to trend to something close to that 65 US cents there in the bottom of just the pure grid. Probably won't get that because I doubt whether all of the solar exporting from residential and commercial solar will be curtailed or tamped down, but you've got to believe it's going to head back somewhere up to 65 cents. So, the grid apocalypse is still here. We're still boiling, and we're way away from the 15 cents a kilowatt hour. So at the moment, the talk is that batteries will solve it. And I guess the most contentious piece I'm going to put here today is I don't think they will. There is no Moore's law for batteries. This is conflating something from the computer industry. And I worked in the computer industry for 20 years, and there's no Moore's law in the battery business. Moore's law came about from the number of transistors fabricated on a silicon substrate. That's got nothing to do with battery manufacture. So the improvement came from being able to put smaller and smaller computer chips together. So there's nothing like that in batteries, just chemicals. So it doesn't exist. And you look at a typical production curve, cost curve for batteries, and it's purely around scale. And after about 1 gigawatt hour of production, you're pretty much approaching at horizontal asymptotes that are totally derived from the raw material cost. Worse, the life cycle of most of the existing lithium-ion batteries, when multiplied by those production costs, they don't work for 15 cents a kilowatt hour. They just don't. If you plug you plug in legitimate cycle life numbers for batteries, this is the 80% of original capacity with the costs that you're achieving now in the marketplace, and because there's a lot of vendors that are already operating in that 1 gigawatt hour of production capacity or higher, you still won't get to 15 cents a kilowatt hour. You'll be way off it. How can we get there? T-cell can, because it has a 20,000 charge cycle capability. So it may be operating with very similar, maybe slightly higher production costs than the other lithium batteries because it's using lithium titanate rather than carbon on the anode. But combined, the benefit of using that lithium titanate is a 20,000 cycle charge curve. So, put those things together in a tool like like HOMER, and you can start to see 15 cents a kilowatt hour, which is my ideal. But before we move to the final part of the presentation, I just what's history if it's not revised? So let's take that 15-cent kilowatt hour, and as I showed, that's really the point of that graphic was really to be 15 cents or less, right? But there's another implication as well. It was taken from a survey of electricity rates around the world, which are backward looking. So really to get a fair rate to assess, we need to account for energy inflation and the discount rate. So my take on this, energy inflation should be low at a background rate, about 2%. But we probably need to learn to live with low interest rates. So discount rates are going to be low. So the ideal rate now, that ideal rate was never really just 15 cents fixed, was it? It was going to inflate over time in some way. But I think if you take that rate and mesh it together with the most likely inflation and interest rates in the future, you get something that looks a bit like that. So 15 cents is still the target. Lower would be better. But I think in certain situations, a little bit higher number can work because, again, think about it. In a lot of these situations where we're using batteries, we're pulling forward the cost, we're fixing into the current time, and it really eliminates inflation. So if we can get that 18 cents with a battery solution today, with a T-cell solution, in fact, then you've pretty much achieved the ideal. And I validate that with HOMER. I validate it here in the regional New South Wales, Australia, both in HOMER and then obviously in practice in our projects. And what you can see is if you take a fairly standard configuration, which is, the details are there, but with a fairly standard configuration, we're within the target zone. 17 cents a kilowatt hour is quite achievable, stand alone. This is not connected to the grid. So yeah, there's icing on this cake. Reality is we still have the grid. If you plug a T-cell system into the grid and getting even some export tariffs, then you're going to do way better than this. So it's a bit of a buffer for the future. But if things fell apart, the grid disappears, or you want to start up where the grid isn't, you can still achieve a worldwide ideal number, 15 US cents a kilowatt hour. We're small. These are practical numbers out of validated out of HOMER in real life installations. I'm not worldwide yet, but we have a worldwide audience here. So what I did is I plugged that same model into a range of other locations, with the T-cell parameters. And this is what I come up with, a pretty interesting Christmas tree. So again, theoretical, not proven. This is telling me that a majority of habitable places in the world, you can achieve that ideal cost of energy on par with legacy centralized industrial scale nuclear and fossil fuel. You can now achieve that decentralized with solar and T-cell. A couple of locations you don't, and you run out of time, but I think you could probably tweak that basic model. You can put a bit more solar, do a few other things, and you could get a couple more across the line. So the majority will achieve the 15-cent target range. So that's my message for today. We can now complete the energy efficient stool. We have the historically proven nuclear and fossil fuel centralized grids that produce affordable power. We haven't been able to do that with renewable as proven in Australia with all of the huge uptake of solar. but now we have a pathway. So by adding long life, 20,000 cycle T cell, we can achieve 15 cents a kilowatt hour energy for consumers in many parts of the world. Thank you for your time today.
Thank you, Michael. I'm Brian Ballack. I'm a commercial analyst at Infinity Energy Systems, and I'm here to tell you a little bit about vanadium flow batteries and how they may impact your work within microgrids. Specifically, I want to talk about some recent advances in vanadium flow technology, a couple of pricing trends that are changing the landscape, some optimal use cases that would make you want to explore vanadium flow as your battery technology, and finally, some practical tips when you are modeling vanadium flow batteries within HOMER or HOMER grid. For those of you who may be new to the technology, the flow in all flow batteries comes from the fact that they store energy in a fluid aqueous electrolyte. Pumps cause this fluid to flow through one or more stacks where the charging and discharging occurs. Vanadium flow batteries, or VFBs for short, are somewhat unique in that they don't rely on a reaction between two different electrolytes in their respective tanks. Instead, they exploit the ability of vanadium molecules to hold up to 4 electrons. This allows them to use the exact same substance in both of their tanks. As a result, vanadium flow batteries experience almost no capacity fade over time. They also require very little maintenance and no replacement over the course of a 25-year system life. There are two trends worth noting in the world of flow batteries. The first is the recent move towards modularization. The earliest and still biggest flow systems were one-off custom-designed solutions built on site. That model proved too susceptible to economic shocks, encouraging flow battery manufacturers to modularize their solutions, making them easier to permit and install. You can see some of Infinity's modules on the right-hand side. We're still working on the ideal module size. If you move all the way to the right, you can see that we're now beginning to package 6 of these modules into a 20-foot shipping container, which is the new building block for systems such as you'll see on the right, which I'll be talking about later in this presentation. This move to modularization allows them to be installed with minimal site preparation and much easier permitting. The other interesting development in flow technology is that vanadium flow batteries are spearheading the move towards safer and in particular non-flammable energy storage technologies. While lithium batteries do manage the risk of fire and explosion with additional system components, vanadium flow batteries simply eliminate that risk. Due to their non-flammability, Infinity's VFBs were recently exempted from the flash ignition test otherwise required for UL's 9540A energy storage system certification. This radically challenges the idea that deploying energy storage means taking on fire and explosion risk. As fires and occasional battery conflagration events continue to make headlines, we're starting to see increasingly pointed questions and stricter compliance requirements, both from permitting agencies and in corporate requests for proposals. In addition to issues of fire safety, there are 2 pricing trends that are now driving more microgrid developers to take a look at vanadium flow batteries. One of these trends is the ability to bundle 20-year parts and support contracts into the initial system price. Thanks to the absence of degradation and the absence of any need for periodic system replacement or augmentation, this means that VFBs can be offered with a built-in 20-year warranty, matching the life of the solar power array. In the USA, federal and state tax incentives, such as the 26% federal investment tax credit, or ITC, and accelerated depreciation schedules partially offset these upfront costs, making 20-year system contracts highly attractive. In addition, market incentives in some states, such as California's self-generation incentive program, now require evidence of maintenance contracts going out at least 10 years in order to qualify. But the more exciting trend is the launch of electrolyte rental. Because the vanadium electrolyte does not degrade and can be redeployed or recycled after the project is finished, parties interested in long-term stable returns can rent it to the system owners, reducing upfront cash lay by about 30% and spreading the electrolyte costs over 10 years or more, after which the rental agency, not the system owner, is responsible for electrolyte recycling and redeployment. The first of these agencies is Vanadium Electrolyte Rental Limited, or VERL, who have inked a deal to rent 5 megawatt-hours of electrolyte to EDF Renewables subsidiary Pivot Power. While parties like VERL are likely to focus on large systems for now, we expect that they or their competitors will begin expanding into smaller microgrid systems in 1 or 2 years. And now let me say a couple of words about the optimal use case for vanadium flow batteries. Some of the characteristics are common. You'll recognize them from your existing projects. The ability to oversize PV so that you've got some surplus generation that can be stored, high energy and demand charges outside of prime PV hours, setting up a revenue stack for demand charge reduction, the need to use generators, either for grid reliability issues or for overnight load, but at the same time, concerns with using generators, be it the maintenance that they entail, the reliability and cost of fuel supply, or perhaps even generator runtime restrictions in your area, whether it be for emissions or noise or fumes. But there are some factors that specifically favor the use of vanadium flow batteries in your projects. One of these is the need for frequent and deep cycling. If you're seeing a project that is indicating a need for the battery to cycle more than 300 times a year for over 2 hours each, or 600 cycles a year at less than 2 hours, and in particular, if the model is seeing the need to discharge the battery down to 100% depth of discharge, this is when you want to start looking at a vanadium flow battery due to its very, very low degradation and its ability to run at that very deep level of cycling without any effect on the warranty. Another major indicator is if high daytime temperatures are expected. Vanadium flow batteries, most flow batteries, but vanadium flow batteries in particular, have a very large thermal mass. This mass cools off at night, and during the day when high temperatures are expected, very little additional cooling is needed. A modest fan load blowing air over the internal electrolyte stacks is enough to keep the battery cool. And that leads me to the next major indicator, which is if you are in an area where you're expecting a significant level of fire danger. As I mentioned before, vanadium flow batteries are non-flammable and were recently accepted from the UL 9540A flash test standard. What that means for customers is that they do not have to worry about taking on additional risk of a conflagration event that injures people or potentially starts yet another California wildfire because the battery couldn't handle the cooling loads for aggressive cycling on a hot afternoon. And finally, I want to talk about a few tips that I've developed over time modeling flow batteries in HOMER. First of all, because HOMER reduces everything to cost of energy, it is very, very important to make sure that the battery is being modeled properly and the costing that you are feeding to HOMER is complete. It's important to note that vanadium flow batteries behave differently than lithium batteries, and these differences do add up to influence project economics. Were you modeling a project with 2 different potential lithium batteries, it would be acceptable to be perhaps less than complete on some of these issues, as you could realistically expect them to affect both batteries to roughly the same degree. That unfortunately no longer works when one of the batteries in your comparison is a vanadium flow battery. In this case, it's important to get a full accounting so that you can make an apples to apples comparison. The best way that you can do that is to contact the OEM for a properly configured HOMER library object that utilizes the idealized battery model. It's not acceptable for you all to have to figure this out in HOMER. There are enough intricacies in the parameters of the battery file that it really should be the vendor's responsibility to supply you with a properly configured library object. Secondly, in order to get complete costing, you do need to get a full all-in quote from the vendor, including both the capital expenditure and any operation expenditures going out over 20 years. One needs to include the cost of a 20-year O&M contract, as that is now becoming the benchmark standard, both due to the life of PV and the increasing visibility of flow batteries entering the market with 20-year built-in contracts. And finally, if one of the battery technologies is a flammable type, such as lithium, then it's important to do the due diligence and find out what the additional cost of any fire prevention and suppression systems is what the effect may be on the customer's insurance premiums, and what, if any, modifications are necessary to make sure that the fire prevention and suppression systems identified have been properly integrated with the lithium-ion system. While you're modeling, there are some features that HOMER thankfully provides that are very, very useful and worthwhile employing in your models, even if you haven't used them before. And so I want to give a shout out to HOMER for doing some of these features, one of which is temperature impacts. They not only impact the ability of PV to produce, but a battery module properly configured in HOMER also has the ability to take account of temperature impacts. So if the lithium-ion object that you're modeling does not have this ability enabled, you probably want to find out why. If the feature is enabled, you do want to turn it on so that any high temperatures used in that site are properly reflected in the ability of the controller to dispatch the battery system. Another thing that really helps is if you can get more granular information about the temperature of the system. While modeling today, I did notice that when I use HOMER's feature to download temperature information from the internet, it seems to show up as a vertical, horizontal rainbow pattern, so that the temperature changes by month, but it does not seem to vary by time of day. In order to get the most accurate possible estimate for customers, it's very, very convenient to get more granular temperature data than that, that actually takes account of the variation by hour of the day. This isn't always easy to do, but I've had good luck getting climate data off of sources like Wikipedia and weather.com. The next shout out I want to make is to the sensitivity feature, which HOMER does very well, and I have not yet seen in most of the modeling tools. Although it does increase the modeling time, I encourage you all to make liberal use of the sensitivity testing feature. You can use this on the battery replacement costs, on the cost of battery maintenance. You can use it to vary the degradation rate, and you can use it to test the minimum state of charge. With flow batteries, this is relatively easy, as you can discharge them all the way down to 0%. With lithium batteries, it's well known that a certain level of reserve is necessary to protect battery health. And that reserve can be dependent on the use case as well as the temperature regime of the site. So as these things are very, very hard to know up front, it's very useful to run sensitivity analysis that tests what will happen if the base case scenario turns out not to be what actually applies on site. Finally, I encourage you all to take a closer look at the way that HOMER records the maintenance cost, both for flow batteries and for lithium-ion. The ability to track maintenance either on a calendar basis or on an operating hour basis is extremely useful. In the case of flow batteries, it's a calendar-based mode. So when you look at a Infinity flow battery object, you'll see that our maintenance tends to be triggered on number of hours in a year. With a lithium system, chances are you would be more accurate going with an operating hours mode, and if a battery cycling mode were enabled, that would be more accurate still. But I will leave it to the experts at HOMER to decide whether that is something that can be done at acceptable levels of performance. And that's all I've got for now. With that, I will return it to the next presenter. Thank you.
Thanks, Brian. My name is Duncan Campbell, and I lead project analysis at Scale Microgrid Solutions. And today I'm here to talk about standardization. I think it's a topic that's come up a lot in the microgrid industry recently, and for very good reason. But what I want to do is, in this quick presentation, kind of take a step back, zoom out, and think about what does that really mean, and why should we be doing it in the first place? And I'll start with just energy resilience as a topic overall. It's why we're all here. It's why microgrids are interesting. You know, we've had a number of events this year that make us think about energy resilience, whether it's the hurricane in the Northeast that left 6.4 million customers without power in New York and New Jersey and Connecticut and Pennsylvania. And always remember, one utility customer is roughly about 3 people, so that's 15 million people. Or whether it's the California rolling blackouts that resulted from a supply shortage during a heat wave that left over 225,000 customers without power, or Hurricane Laura in Texas and Louisiana, leaving 800,000 without power, or Hurricane Sally in Alabama, Florida, and Georgia, also leaving over 500 customers without power. And then lastly, of course, the California public safety power shutoffs. This being an event where we need to turn off the grid proactively to reduce wildfire risk. This has already started this year as well. We've had 2 events so far for which affected 225,000 customers. And of course, the elephant in the room is COVID. Now, it's not an energy resilience concern exactly, but I do think it's gotten folks thinking about resilience overall and how they react to unanticipated circumstances. All of this just pointing to the fact that energy resilience is top of mind in 2020. And of course, all of us here know that for many, microgrids can offer a superior resilience value proposition relative to traditional solutions. You know, there's 3 elements to this. First is about utilization, right? When a microgrid isn't being used for backup power, it can be used to reduce your costs or produce grid services revenues. This idea of utilization of assets driving attractive economics it's the underpinning of the grid itself, right? It's what Sam Insull really pioneered when developing the modern utility model. A simpler way to put it is the grid has always needed some customers to have backup generators and the grid to have peaker plants. If we can do both of those activities with one thing, obviously there's going to be attractive economics associated with that. So this utilization point then flows into the next, which is when a microgrid system produces positive economics, your incentive is to try to deploy more of it, more incremental kilowatts until the point where you hit diminishing returns and you hit some cost optimal solution. Whereas with traditional backup generators, because they're all cost, it's just the cost of buying it, fueling it, and maintaining it, your incentive is to reduce capacity as much as you can, which of course, you know, leads to you with a really fine-tooth comb thinking about what exactly your critical loads are and, you know, how much you can value engineer this thing, really leading to reduced capacity. So first we have utilization is superior, leading to better economics. Then we have typically more capacity associated with a microgrid than a traditional backup generation solution. And then the last point, of course, is diversification, right? When you have multiple sources of energy on site, any one event can happen and perhaps you have other systems remaining that you can utilize. So perhaps with your traditional diesel backup generator system, you have a sub-base fuel tank, maybe it can last 24 hours and you're really just hoping that's all you need, and getting fuel deliveries is often harder than we think. Whereas with the microgrid, perhaps you have that generator, but you also have solar and storage. So if any event like that occurs, at least you have the solar and storage to provide your most critical loads. Or if it's a cloudy day, you still have the generator, right? So this diversification also really buttresses this value proposition. But it leads to the obvious question. If all of this is true, if I'm not lying to you right now, why, even in the most attractive markets, are backup generators still the dominant energy resilience solution? And my thesis, and our thesis at Scale, is that it's mostly about what's being offered to customers that's not captured in the spreadsheet. It's about that microgrid project development process and product. And ultimately, the whole thing, it takes too long, it's too expensive, and it ultimately creates excessive project risk. So let's think about for a second the typical microgrid project development process. Let's say you're a refrigerated warehouse, so you're not a big industrial or institutional client, but you're also not, you know, the pizza shop around the corner. You're a large commercial business that maybe is about to procure a megawatt or 2 megawatts of diesel generators and wants to know what a microgrid could do because you've heard all of these interesting things about it. Well, first, you're probably going to pay a consultant, right? This is outside of your ability to evaluate. And that consultant's going to determine, you know, if there's an opportunity or not, kind of get an early stage go, no go. Let's say you get a go and that consultant or engineer begins to come up with a conceptual scope for this project. So, you know, this much solar, this much battery, this much generator, here's what the control system will be, here are all the use cases being used to save you money, and here's how island mode will work. They'll come up with this project concept, and then it will be time to bid it out, whether that's through a formal RFP or just an informal competitive process. We'll start pulling all the levers we can to push down CapEx. So we'll get bids from a bunch of different generator suppliers, a bunch of turnkey solar installers, a bunch of battery energy storage system OEMs and controls integrators and general contractors. And what we'll end up with is a system that maybe is a few percent lower in CapEx than we originally anticipated, but, and this is the most important point of my presentation, we're now building a first of its kind system. This is a system that has never been integrated before, and this comes with numerous downsides, which I believe is what ultimately hinders our market from addressing the energy resilience problems for those it has techno-economic feasibility. So those problems, include things like projects taking longer to build and going over budget, commissioning taking a very long time, and things never really working quite right. Ultimately, project economics not being realized during the operational phase, and things like equipment failures or the resilience and island mode sequence, taking a lot of tinkering to get perfect. And ultimately, it's just an underwhelming experience for the customer. And I think customers can kind of sense that's what they're getting into when they are procuring a custom engineering construction project. So what this also means then is there's all this risk in the deal, right? And financiers know this, so they charge a higher cost of capital. General contractors know this, so they have more contingency right throughout the value chain. Because this custom one-off first of its kind system is seen as risky, we have to be conservative to counteract that, which ultimately hurts the value proposition to the customer and means fewer microgrids are sold. And that's how we end up with lots of diesel backup generators in places where the economics could work for a microgrid. So what I would say, and what we would say at scale, is that to address the mass market, most customers, we need a solution that is as productized as possible, because few of these customers really have the stomach to engage in that custom engineering process. So to put this more simply, standardization, it can improve the microgrid development process and ultimately the value proposition that's delivered to customers. And there's a lot of ways standardization can flow through a microgrid business, but I think there are 3 key points that any business offering this to customers needs to hit. First, we need to constrain the surface area of the design optimization problem. What this really means is, if once you've collected data from a customer, once you understand their site and you understand their goals, if you consider every possible component of a system, the surface area of that design problem is massive, right? And it's impossible to standardize, and you'll always be offering first of their kind solutions. So what we would suggest is our industry and those of us providing these services to customers pre-select a number of pieces of equipment and controls and solar inverters and battery energy storage systems, pre-select these things and do all the work of figuring out how to integrate any combination of those across their size range before you ever pursue a project, so that when you put something in front of a customer at that early stage proposal, you're certain you can stand behind it and you know the results it will deliver. Then second is about integration, right? So if you do part 1, you create the opportunity for standardization. But then to actually unlock the value that standardization brings, you need to be deeply integrated across the value chain. What I really mean by this is, let's say you're a microgrid developer and you figure out how to deploy these sort of standardized modular elements of a microgrid. And one consequence of that is now we can be much more certain about project timelines and budgets actually being met. In theory, that means the financier of the project should be more comfortable with it and should be able to apply lower cost of capital, thus lower rates to the customer, thus ultimately a better value proposition. But if the microgrid developer and the financier are separate entities that don't share that thesis, well, that value that's unlocked by standardization isn't going to be realized, right? And so by integrating across these parts of the value chain, standardization can actually produce value that actually flows to customers and gets more deals done. And then the last point is you need the company to have tools and processes that reflect the above. You know, if point one is about creating standardization, point two is actually about capturing that value, point three is about making it actionable. So having a BD team, for example, that has a checklist of the standard items they're supposed to go through, having models that already have all of the component data and costs and integration for all of those different modules all ready to roll, and an optimization engine that can take the inputs, take the component library and the tariff library and all of this, and blend it all into, here's the optimal project for the customer. And then, of course, having processes such as the contractual process. You know, often because these projects are perceived as risky, we have all these mile markers and buying down of risk. But once we have standardization, we can streamline a lot of those processes and make for a much better customer experience. So, but again, the point being, if point one is creating standardization, point two is actually unlocking the value that standardization brings, point three is about making it actionable throughout your business. We think if you do these three things and really focus on standardization, we can actually see it get to a point where microgrids are being bought rather than being sold, where they're attractive products for customers, not grueling one-off engineered solutions. If this is something you're interested in, this point about standardization, you know, please feel free to reach out to me or anyone on my team. We love to talk about this stuff. You can find us at scalemicrogridsolutions.com. Thank you, and now on to the next presenter.
Thank you, Duncan. My name is Peter. I'm working at company Bauer RE as energy storage specialist, and today I would like to tell you our story about our approach to reach carbon-free construction sites for our solar parks. My talk is structured that way that I will first introduce you to the topic itself and the situation on our sites. Then how have we worked to come to our solution for a clean mobile energy supply for construction sites. And last, I would like to share the learnings, especially technical learnings, also do a quick cost comparison and the way forward. So why carbon-free sites? Well, there are different motivations for this topic, but first of all, we are a renewable energy company that realizes solutions in different way. So for this presentation, it's about the solar park construction sites. But in general, we would like to avoid fossil power wherever possible. And for the solar park, for us, the biggest trigger is there starts during the construction. So that's one of the triggers. Next, we can see now today already that the first countries introduced already stricter and stricter regulations for the building sector regarding CO2 and NOx emissions. So on the right-hand side, you see here for Netherlands, which introduced quite strict restrictions for the building sector in 2019. But also Greater London area wants to reduce the stepwise the emissions on construction sites to finally zero emission machines. Besides these external factors, we can look at the genset itself and see that we have a quite low fuel efficiency, especially for low loading, which we often see on construction sites. So here we are at maybe 15% or sometimes even less of fuel efficiency, which is not very motivating to use it. And the next topic is, if we are talking about a bigger construction site, which is there like for maybe 3/4 of a year, we do need to assure a constant fuel supply for these sites. That means there is a constant effort of logistics and also of costs of a month to assure that there's enough fuel. And a quick comparison to the sun reveals us that, well, the sun delivers us the fuel, the sunshine for free, and also sends no bill. So here's another motivation. Next is O&M cost. For gensets, as a mechanical component, of course, there's higher O&M effort, especially for systems which are in use 24/7 on site. So PV batteries have quite lower O&M effort here. Next is contamination, and this is quite interesting because the sites get regularly inspected. external persons, so external inspectors, review our site, and we feel that they take closer and closer look on possible ground contamination due to spilled fuel. And they are quite happy to see if one of our sites has already a solar and battery energy supply, because this is getting more and more strict regarding possible ground contamination. And last but not least, also a big motivation is for our staff and our colleagues on site, that the sound emissions due to gensets make the working environment actually worse, because they are usually located quite close to the containers, to the office containers, and for the break time areas, and therefore a quiet solution is also much appreciated by our workers. So how does actually a site look like? I brought some impressions along. You see here on the right hand side a PV floating construction site. It's actually the biggest PV floating site outside of China, 27 megawatts in Netherlands. And there's just a PV puzzle which will soon be moved over the complete plant. And here in a closer view, you see the construction line, and there's quite some action going on to produce that plant. And on the other two pictures, we see a typical ground-mounted construction site with here the ground open right now and connections going on, and a typical power supply for such a system. So the status quo was that these sites were supplied by diesel gensets, because of course during construction site time there's no grid connection yet. So usually there was a 30 to 660 kVA genset, including fuel supply system, as visible here on the left. And when we would like to transform that to a renewable supply, the first question is actually how much is the consumption, the electric consumption, the load on site. And this was not an easy question to answer, because when we answered colleagues, okay, what do you guess, how much is load consumption on the sites? Well, they said, okay, for bigger projects, we have gensets of around 60 kilowatts, so consumption will be 20 to 30 kilowatt in average. But actually, we didn't really know about that before we started measuring if that assumption here is right or not. And looking at the load, okay, you can see here from a ground-mounted installation in Southern Europe, there are some containers with cooling. We got the charger bank for many tools, charger banks for the hand tools. There's cooling and refrigerating for food and drinks necessary. And for the northern sites, let's say in wet times of the year, there's also a load which shouldn't be underestimated, which is drying of wet clothes overnight. So, but coming back to the 20 to 30 kilowatt average, well, measuring showed us that we are like factor 10 too high here, and that the actual consumption is only around 2 to 3 kilowatt in average during the day, as visible here on the graph, and as a maximum around 20 kilowatt for some high peak consumption. And the kilowatt hours per day differ here between 20 kilowatt hour up to like 50 kilowatt hour on the long run. So after that, after knowing the consumption, we did write down clearer requirements. What does such a mobile system actually require to do in our point of view? So what does it need to fulfill? And therefore we also looked at the market, and we found that there are already some mobile hybrid PV battery diesel supply systems on the market. But for our impressions, these systems only included some PV panels that maybe guaranteed a visual green impression, but at the end, they wouldn't supply our loads with green energy though. So our approach here was different, and we said, okay, BayWa RE will not even include a genset in the solution. If we want to build solar, then we want to build it 100% with solar. And therefore we derived the following requirements. We need to be able to include PV AC systems, since they are anyway on site. We want to use the modules and the inverters later for grid feed-in, so why not using it directly during construction? Since the inverters are not always there at the beginning, but the modules are, we also need to be able to integrate PV DC-wise. We do not want to send out a specialist if there's a problem, so remote monitoring was important for us. Also, the system needs to be able to move from one project to the next, so the size and the weight and the transport regulation due to the batteries was quite an important topic for us as well. And looking at smaller projects, bigger projects, projects in Southern Europe or in Central Europe or anywhere else in the world, the solution needs to fit for the size of the project as well as for the period of construction, be it summer or winter, and therefore also different locations of construction, so different climate zones. Looking forward, we have the strategy to more and more electrify the sites also on the machinery view. So electric machinery charging is also a requirement for the future. And all the thermal loads, this heating, cooling, and drying needs, they really put pressure on the electric consumption. So this is quite a hard requirement to really fulfill all these loads. After that, it went to the planning process, and it all started, of course, with simulation and sizing. So after measuring and estimating the load on site, we sat down on computer, varied the seasons and the climate zones, varied the location, varied the PV charging power and the battery storage power and energy capacity to find out what is the minimum requirement that our system would need for that. And fortunately, there is good software out there on the market, so we used HOMER Pro in order to find out about that. And after the minimum requirement system specs were fixed, we went to the engineering process and planned and co-developed the system with our partners and took as a starting point standard products that were available already and adapted them so much that they fit our special requirements to come up with a defined product and components. After that, we moved from the desk to the lab and did a test of this battery in the laboratory with a focus on the PV curtailment and the control principle for the PV on this island grid. So we are always there, an off-grid system, there's never a grid connection. So the control of the PV energy is actually the biggest hurdle to take. And then finally we went out on the site in summer 2018 to Spain. You see the picture here. So on the right-hand side, you see the PV modules, which are kind of mock-up tables, which are designed or built right in the beginning of a project. So that means the modules are there, and there's quite a lot of them, so hundreds of kilowatts. And this is there for free, so you just need to make use of it. And these are then connected to a mobile battery. This is this white block here, and the construction loads are not so well visible here. We see here one container, but there's also more there in the back, the substation load in this case. And then we started to gather experience, and this took us quite a while. So altogether, we tested 5 different mobile battery systems on 10 projects during 3 years. And as you can see on the pictures, we tested as most flexible or as most different as we could. So we tested on PV floating sites, we tested on PV ground mounted sites, we tested in Southern Europe, in Central Europe, in wintertime, in summertime. We also did tests with electric machines, so to have electric forklifters or staplers on site as a new load, which hasn't been there before. We tested the PV AC system integration. So as you can see here on the picture on the right, the floating system usually comes directly cabled with modules and inverters directly. So here it's best to have the possibility to take the pre-installed inverters directly for our charging for our battery system directly. On the other side, the lowest picture here shows the ground-mounted installation. So there you can see there's no inverter yet because they usually come at the end of the project. So we need the possibility as well to connect the modules DC-wise directly in order to assure power supply from the beginning on. So we have this AC integration and DC integration. We tested different battery chemistries. So we tested lead-acid batteries, we tested lithium-ion batteries. We went for very small system from like 20 kilowatt hours, 30 kilowatt, up to half a megawatt hour or 60 kilowatt hour of battery power. We went for purchase models and also rental battery modules and tested rather low cost to high cost solutions as well to get a good overview. So what were the learnings that we draw out of that? Technical learnings. You see here on the right hand side the schematic, the system schematic, and this green-gray box here shows the battery case with the battery inverter, battery modules, and also a built-in PV inverter. And as I explained, we have the possibility to install for floating sites, inverter and modules directly connectable. For ground-mounted sites, we connect the PV modules DC-wise to the built-in inverter. And we also have the possibility to directly DC-DC connect the modules to the battery. I'll explain in a minute why that is important. But first, let's focus on the learnings. What were detected areas for improvement? We found out that for us, the frequency control of the PV inverters is a too rough control mechanism to really control the PV curtailment, because these grid-tied inverters, which are used for the solar parks, are not really designed for that off-grid operation. Next is that the lead-acid battery SOC estimation is too inaccurate over time. So the SOC estimation drifts apart after a while, which is not really suitable to have reliable SOC information. The maximum connectable PV power for charging our battery was too low in the beginning, and also the battery capacity was not enough. And what's more is that the charging took us way too long. You have to imagine if we are in the winter period in northern Netherlands, for example, you're quite happy if there's like 1 or 2 hours of sun during the winter, and you really need to make sure to use that sun window to charge the battery as much as possible. So these improvements we did implement over time. We switched from lead-acid systems to lithium-ion. We increased the battery capacity 3 times regarding the pilot. We enabled fast charging capability to have a to reduce the charging time from like 10 hours down to 2 hours. We moved from frequency control to direct component communication. We implemented a PV 0 feed-in mode for these grid-tied inverters to have them still on the grid, but not producing any energy in case of a full battery and no more load. And as I explained before, the DC-DC connection is quite important, because what do you do if you wake up in the morning and your battery is empty and you want to start it up? There's solar energy, but still your battery cannot start up because the 50 Hertz is missing to have these PV inverters running. So in this case, you would always need an external grid, an external genset, or some AC source to really start your battery. So that's why we included the DC-DC connection to have a black start capability in case of an empty battery. But the biggest tackle were actually the cloudy winter days. Since, as I explained, we want to run 100% on solar on any condition, these cloudy winter days are quite challenging, and therefore we designed 2 solutions. First one is including that PV-AC system for the floating sites with external control. We have the possibility now to connect up to 320 kilowatt peak on only a 45 kilowatt battery inverter for charging. So quite a heavy oversizing of PV versus battery charging capability, but solar power is there. We just need to make it usable. Second option, excluding any control, so quite robust, is the built-in PV inverter that we chose, because here we can realize a DC-AC ratio of 6. That means we can put 120 kilowatt peak of PV power on a 20 kilowatt inverter. And with these 2 solutions, we can generate solar generation curves of this shape here. Like we have a square. That means as soon as the sun goes up, we have full power available, limited to the maximum charging power of the battery, almost until the sun goes down. So we have quite a constant source of energy due to that oversizing of PV. And that leads to a quite smooth operation. You can see on the right the battery SOC for that heavy PV oversizing. During the day, the battery gets hardly discharged. It more works as a buffer for the short moments of shadow. But as soon as the PV kicks in, the battery is directly charged back. And only over the night here we lose, in this case, like 10, 15, 20% of charge, until in the morning we get right away charged again. So quite smooth operation. I would now switch over to the cost comparison. And here I did that comparison for the rental option, because that is where we came from, and assumed a weekly consumption of 240 kilowatt hours. And as we can see on the left-hand side for the genset option, we have, depending on the project size, a usable power of 20 or 40 kVA, and that causes over the project, for a smaller project, 3-month period, cost of energy of around 2.1 euro per kilowatt hour up to 5 euro per kilowatt hour. Whereas with the battery, assuming of course €0 for the solar PV on site because it's there, and the rental cost for the battery, cost of energy of around 1.6 to 3.4 euro per kilowatt hour. That means the PV plus battery supply is for us already a cheaper solution today. And last but not least, for bigger projects, we can eliminate up to 1 ton of CO2 per week in comparison to big genset supply. Let's conclude with the vision and way forward. So BayWa r.e. wants to really further electrify more and more the construction sites, reduce the usage of diesel gensets, and combine that with other innovations like, as I said, we would like to move more and more to electric machines on site, which are an additional load to be charged, use also electric vehicles and logistics on site, and to switch to a more, let's say, smarter consumption. So especially for these heating loads like drying clothes, move away from electric heaters and test out dehumidifiers. So we did that already for some winter projects, some wet projects, which bring a factor of 5 in efficiency comparing to electric heaters. And for heating purposes, think of isolated containers for winter periods instead of standard construction containers to reach our target to really build in future solar parks with 100% solar power. Thanks for listening. It was great to have you here, and I'll pass on to the next speaker. Thank you.
Thank you, Peter. My name is Drew Leibowitz from DNV-GL. I'm a senior consultant there. I'll be talking today about bidding batteries, a way to enable bankable storage in microgrid applications. And it's great to be here. First, a quick bit about DNV-GL. We're a multinational company based in Norway, have offices all over the world. Within DNV-GL, I work with the energy team, and within energy, our team is energy storage engineering. We do work on microgrids, energy storage projects, and also a lot of energy access work, a lot of which involves tools like HOMER and modeling microgrids and energy storage. Personally, my background is in energy access. I worked in Haiti for a long time running a small utility company there and did a lot of HOMER work. And here at DNV-GL, we also do a good bit of energy access, as well as independent engineering of microgrid and energy storage projects. Most of that is in project finance of large-scale projects. We also do a good amount of owner's engineering, so developing technical specifications for different types of energy storage assets and microgrid assets all over the world. Today, I want to start the talk with sort of the drivers of microgrids. And at DNV-GL, in a lot of our work that we do, we see the primary driver of projects is how we're going to make money. It is usually large-scale businesses that we're working with that are running these projects, and they want to look at all the potential revenue streams that they can possibly consider. We generally call that the off-taker, whoever would be purchasing the energy. And you'll see on the right side of the screen a list of the few common ways that these projects might make money. So we know for most microgrids, we'll be looking at energy sales, whether that's through a PPA or net metering, demand charge management, so avoiding peaks that happen in peak charges and demand charges, depending on your jurisdiction. There's a big need for reliability. So if either the grid is unstable or goes out, or even places where there is no grid, wanting to have a backup. But there's also some other services that could be offered. We've listed one, distribution system support. So that might be helping the utility or the distribution system as a whole support its operation. But the big one that I want to talk about today is that last one, that's merchant market participation. And we know that in addition to just selling energy, there's a lot of other services that microgrids can provide, and especially batteries. When we have large-scale storage, there's a number of different merchant markets depending on what your location is. I'm mainly today going to be talking about US markets, but these are evolving in Europe and all over the world to really be some of the big drivers of how batteries can make a financial case and make money. I did want to talk about where these types of projects fall. So in the power system, we're talking about the end closer to distribution, commercial and industrial and residential projects. While DNVGL works with a lot of larger scale energy storage assets, we know that for microgrids, usually they're falling on the right side of this diagram. And so that is what I'm going to be talking about today. And I would highlight that that includes both standalone storage projects, so large scale batteries that are connected to the power grid. It includes solar plus storage. So we've seen a lot of batteries being deployed together with PV. And it also includes residential projects, which now are becoming more common to be seen in what we call a VPP application, virtual power plant. So even though each individual battery at a house or a business may be small, those can work together to bid into the marketplace for these types of revenues. So I'm going to talk quickly about market incentives, specifically in the frequency regulation market. And frequency regulation, for those who don't know, is a service that every power grid requires. That's sort of the last fine tuning that's performed on the grid in order to match the demand at any given point with the supply of electricity. Traditionally, there was no way to store energy at all. All the energy that's produced by all the different generation sources on a grid has to exactly match the consumption. But now that we have energy storage, those batteries are sort of uniquely positioned to be able to respond very quickly. In the past, that service had been provided to utilities by gas plants and some other types of assets. But now it's more and more common that they've embraced energy storage, and specifically lithium-ion batteries, to be able to provide those sort of services. Back in 2011, FERC, the Federal Energy Regulatory Commission, ordered that all of the independent service operators, or ISOs, start markets that were developed specifically for storage. That, of course, has taken a long time, but we've come a long ways. Some of the leading markets are PJM, which is in the East Coast, northeast of the US, and also CAISO, which is the ISO in California, have really led the charge. But all the different regions of the United States, also parts of Canada, and then other parts of the world as well, have moved ahead with these types of markets. And what those markets do are allow batteries to supply a service that's frequency regulation, and it gets paid on a per megawatt hour or per megawatt basis, depending on the market, allowing those projects to make the revenue. Some projects do that sort of as a side gig to make a little extra money on top of their existing operations, and others, it's the main way that they make money and justify themselves. And a quick update from very recently, in September 2020, PJM, one of the leading markets in the US, voted to use an ELCC method, which is, it's fairly technical, but what that means is another way that storage can participate in that VPP, or virtual power plant application, meaning more opportunities for batteries to make money in these markets. So knowing the market is out there, merchant revenue can be considered on an iterative type of basis. So using a tool like HOMER, we might size the types of batteries specifically for the project that we were working on. So if it was a resiliency application, we might have them sized for whatever outage might take place, or if it was a solar plus storage application, we have them sized based on the ideal configuration there to support the solar. But what we find often is in many of these different applications, the batteries are idle, meaning that for many hours out of the day or even days out of the year, your batteries are fully charged waiting for an event. And while that's good in the sense that they're ready to snap into action when we have an event like that, it's bad in the sense that they're sitting there and not making any money. And so using some of these markets, batteries that are idle can take advantage of the fact that they're there and they're connected to the grid, and supply some of those services to the grid for additional revenue streams. Now, just to be clear, the sizing on this, it has to be fairly large. This is definitely, we'd be talking usually at least 5 to 10 megawatt hours and up. So usually container scale of batteries. So this is not something that's going to be done on small isolated microgrids. But given that virtual power plant application, it is something that we're starting to see where companies will group together many residential batteries or commercial and industrial batteries and use those to bid into the markets. So given the HOMER outputs or whatever modeling tool is being used, we can then take those outputs and use them as inputs into an analysis that'll consider, for a given energy storage system, how can we take the idle time from those batteries and use them to make money? So we would input all the different model parameters. In this case, this was a DC coupled storage and solar PV application. This one in particular was looking at the New York ISO market, but you could really analyze this for any market. And then we put in all the parameters similar to using HOMER of all the parameters that go into the system. And what comes out the other side is that we're able to look at the amount of money that could be made by the system in a given market. So this output here, if we look in the lower left, we see that the purple line is cumulative energy saving. So that's traditionally what might come out of a HOMER type analysis, where we would see how much we saved either by avoiding demand charges or by selling energy back to the grid. But we also see the teal line, which is Reg D revenue. Reg D is the name for the frequency regulation market in PJM. And so in this case, we see that that revenue is steadily climbing and looks to be about a third or so of the revenue compared to the energy revenue coming from the PV, or about a quarter of the total project revenue. If we look at cumulative energy savings, this is just a one-day analysis, but we could perform this on any given month or year. We see that that asset is making about $58 in savings from its energy production, but $20 from the Reg D market, which doesn't seem huge, but if we multiply that over the life of the system, we're talking about thousands of dollars per year. And then if we do that on an MPV basis, just the same way HOMER does its analysis, we can see that it really starts making some of these assets more and more profitable. Of course, this varies based on which market you're in. And really has to be looked at in that context. You can see at the top left, the price varies. So it's not a set price you're getting for the kilowatt or megawatt that you're bidding in, but that price is going up and down over the day. But it does start to constitute a great financial proposition for this battery. And of course, some of these can be used at night, which is nice because we know PV in the evenings is not producing anything and our batteries are generally full. And so we're able to use those. Use the benefit of having those batteries in the system. Lastly, we're going to look at, just like HOMER, we could take a look at the IRR or internal return that we would get on this type of system. And it allows us to do a cumulative analysis of all the revenues over the course of the lifetime, balanced against the capital costs of that system. And then just like HOMER, we can compare that to see what kind of return we're getting. Just recently at DNVGL, we did one looking at a fairly large battery replacing a gas turbine, and that ended up having an IRR over 10%. So it was a pretty attractive financial proposition based on the PJM market that they were participating in. Looking forward, so the big trend we've seen in battery costs, you can see this model going from 2008 to the present. We've just seen them fall and fall and fall. Anyone in California probably knows Aliso Canyon, which was a big gas leak that was used to spur on energy storage because they wanted to replace gas plants. And back in 2016, we were seeing prices around $550 a kilowatt hour for energy storage. Those prices today in 2020, now these are for systems that will not be installed for another few years, but we're seeing projects starting to break below the $300 a kilowatt hour barrier. And that's for all-in costs for energy storage. So it's really come down. That's been a result of the scale of the projects and also the falling battery costs themselves. So over time, we see those costs falling, meaning systems are getting cheaper. And then conversely, the green part of the graph shows the energy storage market, which we see is only growing. We estimate it's somewhere around $50 billion today. And that's continuing to go up and up as FERC and other regulatory commissions around the world pave the way for batteries to participate in these types of markets. So between these two trends, it's really been a real stark increase in the number of systems that are bidding in the markets, both standalone and those involved in microgrids. And we expect that trend to continue going forward as more and more batteries can consider this as a potential revenue source over the lifetime of the system. Thank you very much. And now I'll turn the mic back over to our host.
Thank you all for those very excellent presentations. And I know that the audience has questions. We've already seen a lot of questions coming in. While you're preparing your last questions, I just wanted to let you know that we do have another opportunity that's available for you in association with the conference. You may want to enhance your knowledge even further by signing up for 2 HOMER Foundations training sessions for conference attendees. Next week, we are offering Foundations of HOMER Pro, and the week after that, October 27th through 29th, we will have Foundations of HOMER Grid. Both are 6-hour classes with 3 sessions and 2 hours each, and they are taught by our HOMER modeling experts, so you'll learn a lot about HOMER modeling in those. You can find out more at microgridconference.com/HOMER training, or you can contact us through support@homerenergy.com. And so now let's go ahead and head over to our poll and take a look at how that is going. So far, other storage technologies not suitable for vehicles will become a major player, is leading the way. Hydrogen, though, has definitely taken 23% of the responses so far. If you haven't answered that poll yet, please do go ahead and do that. We'll keep it open until the end of the session, but now we'd like to switch over to questions and begin to ask Peter to join us, and also the presenters. If you would please unmic yourselves and share your webcams, we'll turn it over.
Well, thank you, Tricia. And let me make sure I am unmuted and turn on my camera. Yeah, so thank you, and thank you for all the presenters. Those were great. The last presentation in particular started talking about merchant markets, and I just wanted to put in a little plug for a new piece of HOMER software for FM for front-of-the-meter projects that is available through our advisory services. It's not available as a product for several months more, but we're using it in advisory, so for merchant projects. Well, the question that got the most vote, the 2 questions that got the most votes are actually very, very similar. Have I elevated that? I guess so. How can operators manage to find the optimal battery sizing when the technology is changing so rapidly? At first I thought, well, gee, the answer is HOMER, but I think they're really asking about, well, if in a few years they're gonna get a lot better, how do I think about that? Which is sort of what the second question, does a longer battery life of greater than 10 years have economic benefits to users? Well, I think that's kind of answers yes, but again, it's about given rapidly changing technology and lower costs, maybe we don't want a 10-year battery. Maybe we want a cheaper, shorter battery because we can replace it so it's something better in the future. I used to make that argument fairly often when lithium batteries weren't really were hard to get, and I'm wondering if that's I'm wondering what the panelists think of that. Like I say, I used to make the argument. I'm not sure I still do. Curious what you think. Who wants to take that? And Andrew, Drew, it looks like you're talking, but you're muted. Or Brian, I don't know. One of you jump in. Yeah, Andrew, you're muted.
Might be double muted.
But Brian, did you want to say something while he's unmuting himself?
Well, I just wanted to say this kind of reminds me of the same question we used to get when when laptops first started coming out. Why buy a laptop now when the technology is rapidly changing? Or why not get the cheapest laptop you can get now and then change it every couple of years? And I definitely would not want to do that with my laptop or my smartphone, and I would not want to do that with an energy storage installation for the same reason, which is that there are significant disruptions that occur when you go into an existing system and try to make changes. On the energy storage side, especially if it's a grid-connected microgrid, you've got issues related to permitting. There may be a net energy metering contract that's running. And when you attempt to go back and make significant changes to a system that's already under an existing contract, all kinds of unintended soft costs occur. On top of that, if there's any system replacement that needs to happen, you can't assume that it's going to happen instantly when it's needed and that there will be no impact to the projected revenues or avoided costs of the project while you're waiting for that replacement to happen. Every time a replacement has to happen, there's a risk that it won't happen soon enough, that the equipment that is now available to you is not 100% compatible with the installation where you want to now site it. It's taking on a lot of risks that you don't have if you've got a battery that lasts. And so I recommend to customers what is always recommended to me from IT professionals, which is get the best battery system that makes economic sense for your project and ensure that it will do what you've tasked it to do for as long as possible.
Can you hear me now? Okay, great. I would just add to that, that really covered a lot of the points I was going to say, but we see a lot of augmentation strategies. So when the projects are getting financed, we really have to have a complete picture of what the expectations are, both how many megawatt hours are going to be added in a certain year for under the warranty. Usually it's based on the warranty for the original system, and all the different augmentations. And usually see 2, 3, 4 augmentations maybe over the course of the project life, which is usually around 20 years. But I would say that because we know battery costs are falling, the trend has been to have more augmentations, meaning to barely squeak by as the capacity of the system degrades. So it'd sort of be a both response. So you'd have systems that last a long time. We're seeing either 15 or 20-year warranties are pretty standard, and then also having several augmentations. So trying to leverage the fact that the costs are going down over time.
Another way to answer that we've found is when deciding on perhaps using a more expensive battery that can last longer, or having a lower depth of discharge to help the battery last longer. That cost optimal solution is heavily dependent on what your assumed cost curve for lithium-ion batteries is over time. If you assume aggressive cost reductions, as we've seen for the past 10 years, it can make sense to wear out the battery faster and just replace it, versus buy more battery up front, have a larger buffer on either side of it, and get lower utilization, but over a longer period of time. So your assumed cost curve ends up being, in our opinion, the key input to your battery strategy over the 10, 20, 15-year period.
I think I would maybe just add one thing to that, which is if you're going to take that strategy, you need to remember that the factors that make you want to replace a battery for performance reasons, or due to approaching only 80% of original rated capacity, those same factors are also increasing your risk of fire events. That's the other motivation for performing a replacement. So if you're following the squeak by strategy, you need to make sure, as you really should with any energy storage system, that you've got a well thought out fire detection and suppression system.
Great, thank you. I hope you all enjoyed the little musical chairs we were playing over here, dealing with connectivity issues. But so I missed some of that answer, but let's move on to the next one. Will battery energy storage systems replace diesel generation completely in the future?
No, I think that's unrealistic. I think that that's unlikely to happen until such time as we've got battery costs across the board that make generators uneconomical. And I don't see that happening anytime soon. What I do see happening is the ability to minimize the size and the runtime of a diesel generator, so that you're not employing a battery, a highly engineered battery, for that last 5% of energy need, or that last 5% of load that you're going to need on a very few hours per year. That's no longer economical. There was actually a great presentation earlier in the week on that. I regret, I can't remember which presenter it was, but he made the case rather persuasively.
I would say it depends. It depends on the application and on the sector. I mean, I know companies that are already questioning their diesel genset for emergency supply and testing out hydrogen solution. Also, I mean, here it's stated diesel gensets. So how about maybe gas gensets? For our construction sites, I would say in the long term, we would really get rid of the genset. Will they disappear completely in the world? Of course, no. I agree to Brian, but I think there will be applications that will more and more get totally rid of gensets. Not mainly, maybe not only for cost reasons, but also for emission reasons, or maybe they're also forced to do it. Stating, for example, the construction site examples in some countries in Europe here.
In the HOMER, we've done a lot of HOMER modeling, obviously, and batteries are obviously better for day-to-day frequent cycling, for frequent use. Where we find backup generation is great for the very, very infrequent, but if you want 100% reliability, you know, you don't want to put a battery in there and this capacity of which only gets used a couple times a year, but gensets are good for that. So it's like Brian said, it's all about minimizing runtime and fuel use. But for that occasional worst case situation, that's where gensets, I think, have a niche. Anybody else have a comment on this?
Yeah, I'm probably the older and more cynical character here on the call. Look, I think gensets are probably going to come into life. I'm pretty excited about electric vehicles. It's taken me a while to get excited about them. I'm more in the stationary storage with the T-cell. But I saw coming through the presentations tonight, some themes that I've seen in my own modeling, and that is with good batteries and with the price of the batteries, you should certainly be oversizing your PV. And that obviously maximizes the use of the PV and the batteries. It does not eliminate that tail end on the solar issues and the demand curves that we're talking about here for generators. But I really think that's where electric vehicles come in the next few years as an adjunct to the system. And I think HOMER is well ahead here in starting to model that. But I can see a case as you know, say the VWs come out in a couple of years' time, at least in my location. You know, there's 70-80 kilowatts of storage sitting there in the house. I probably only need 30-40 kilowatt hours that day. Typically, there's my genset to pick up you know, the low sun day or the high demand event. So you know, as electric vehicles come in and augment existing solar and storage, I do think diesels may be coming to an end.
Replaced by V2G when we get to V2G.
Correct.
Okay. Should I move on? The next, okay, I will. The next question, it looks like it's mostly for Invinity, but so maybe we make it quick, but I think it's a good question. Modularization seems to defeat one of the principal advantages of flow batteries, the ability to decouple energy and power capacity. So.
That is true. Modularization puts an upper limit on the energy capacity. So you're now coupled, whereas you were decoupled before. But what we found is that at least in the current market environment, it's worth it to modularize the system, because those very large custom bespoke systems that some of our Invinity team used to create in predecessor companies, they come with very special one-off, one-time only engineering challenges that make the sites much more expensive to install and more susceptible to economic shocks than the modularized system. So I think that the modularized vanadium flow batteries are going to have their phase now, and we will come to a point where the energy system really wants to have those very, very long duration systems, where you'll start to see companies doing larger flow batteries. Might be Invinity, might be somebody else, but I don't see that coming online for at least the next 2 to 3 years.
Well, another quick flow battery question, although I think other people might be able to answer it as well. But do they compete directly with lithium, or because of the longer duration, they're competing for different kinds of projects?
I'll make this one short. Our short answer, speaking only for Invinity, is they have not been looked at as direct competitors to lithium ion because of the decoupling issue. And so they still kind of have this brand image as being very, very long duration systems. We intend to compete directly with lithium ion.
Yeah, and to build on that, I would say that at DNV and large scale commercial transactions, we have not seen vanadium flow batteries that are competing or being proposed as technology solutions in really large scale projects. We have seen occasionally that it's more of a proprietary solution if a solar company might have that as their proprietary solar plus storage solution, usually on some sort of modular basis. And I would quickly add to the previous question about modular solutions, there does seem to be a parallel there with lithium ion, which would be, we're seeing some systems that are more modular, like a Tesla Megapack, where you have the inverter incorporated in, so you have a specific power to energy ratio, but that seems less common than the decentralized or the decoupled systems, so that you can put as many containers or DC energy behind whatever size inverter you want, and then customize that to the solution.
Okay, thanks. I'll be honest, I'm falling behind on this. There's an awful lot of questions coming in, and I've been trying to filter them. This question, that's at the top of the list there, got 8 thumbs up. So does anybody want to take it on? Or should I just try to find another question here? I did have this one up at the top of the list, mostly because I'm very interested in floating points.
Yes, that's a good question. And thanks also for the critical question. It is certainly a big issue. And we did spend, so I would say, yes, we have evaluated the input quite for a long time. So we came up with more than 3 years of development before the first floating site started. And we've done many visits in China where the first floating sites were built. And we have seen the things which we don't like, which is, for example, dead areas of water where the water cannot freely flow through. And that's why we designed our own floating systems that way. For example, starting that we use special PV modules. We have designed special PV modules that leave more than 20% of the light going through to the lake, making sure that the life underwater still happens. What's more, that there's no dead water for our PV floating sites, so water can flow right through. We are reducing evaporation of lakes, which is in these times also a problem. And looking at, for example, hydropower and pump hydro storage, this can be really exciting in the future to look at floating PV sites on pumped hydro storage lakes. And the problem of environmental issues there is totally solvable. And I would say we really have a sustainable system designed here.
Okay, what about this question about standards for, are we at a point now where we can have standards not just for safety, et cetera, but also for design and for energy management strategies? Something we at UL would probably love to get involved in. What do you think? Is the industry ready for that?
It's a very good question. I think we see a lot of different EMS products, and they all seem to use similar communications strategies, but the way that they actually manage those signals is unique to those systems. So I would say there isn't as much internally to an EMS. I will say when they start talking externally, so the frequency regulation or other types of signals, then of course that has to be standardized to some extent. Yeah, I would say at this stage it's fairly unique, and I think it could benefit from standardization.
Okay. Do you expect flow batteries to scale down and compete in the residential market in the future? And are there other companies doing that?
Yes, they're doing it now. There's Voltstore in Bavaria, Peter, and there's a startup out of the City University of New York, Store N, they're called. They're both doing residential scale flow batteries. I think Voltstore is actually shipping, and Store N is getting close.
There's also Volterion in Dortmund. So I know at least 2 startups in Germany which are specially designing them for residential market.
Okay, a real specific question for the lithium titanate. Can you answer that question, Michael?
Yeah, the LTO is used in the anode. It replaces the graphite, and there is a reduction in energy density. So if you compare that to a regular lithium-ion battery, I'd estimate it about 20% less capacity. So a bit like that earlier poll where I think the #1 question was, will chemistries successful in solar storage be different from EVs? And I think I would assert this is such a case. So yes, it is slightly less energy dense, but the cycle life advantage you get makes it ideally suited for solar storage.
So what kinds of new and innovative business models have been developed to get an optimized battery energy storage system and/or a hybrid solution? Business models.
I would say that the VPP applications we've seen are probably the most innovative. So that would be where you have spread out installations, whether mostly C&I or residential. We've seen some changes in the FERC regulations that basically said that VPPs can bid in to frequency regulation as regular systems, which is a pretty exciting development. It means that hundreds or thousands of batteries spread across a geographical area can operate as a single unit, and sometimes whoever owns those batteries doesn't even know. And so in those cases, we've seen a business model of whoever's financing the project would offer it as a service. So they would come to a big box store or a residence and say, hey, we'll save you this much a month, but we will own the battery, and then use those as a VPP. A pretty interesting new business model.
Great. What about developing, indigenizing these technologies in countries like India, where the CapEx and OpEx is considerably higher for flow battery installations? What kind of developments need to be made to indigenize?
Well, it's not difficult to do final assembly for batteries in a different country. Most of the intellectual property that is difficult to cite in a specific country is in the stacks that sit above the tanks, where the electrolyte actually flows and where the electrons are passed back and forth. But it's easy enough to set up a final assembly in a given country where the stacks come from one location and the rest of the components can be sourced locally. So that's the first issue. If the CapEx is high and the OpEx is high in particular, you want to make sure that you're talking about a pure vanadium flow battery. I neglected to mention that there are different vanadium chemistries, and some of them mix in other elements besides vanadium, and they tend to bring with them additional OpEx issues, because now you've got that reaction happening between the two reactants, and pure vanadium flow batteries don't do that. So that's one way to keep your OpEx very low, to make sure you're talking about a pure vanadium flow battery.
Okay. Excuse me while I get rid of that one. What's the next one? How sensitive is the battery energy storage system industry? What happened there? Oh, I forgot to, sorry. Oh, there we go. Thank you, Marilyn. How sensitive is the battery energy storage system industry to government regulations? Could it be an industry that is consumer based, I guess, without the requirement for subsidies? So how dependent are we on subsidies? How long was that a permanent condition? I think that's the question. What do people think?
I would say, speaking for some countries in Europe, or at least now focus on Germany, that's the other way around. In case we wouldn't have mean, we have kind of solar tax in Germany. That means we pay for every extra kilowatt hour that we consume locally. And if that tax wouldn't be there, and also feed-in tariffs are that low already that feed-in tariffs are at around 7 cents and market price at around 5 cents. So it's really close of having really no subsidy anymore. And taking that solar tax, I would say if there would be no regulation at all, no subsidy, but also no tax, then they would be economic today already. Depending on, I mean, for residential, yes, it's economic today already. For commercial and C&I, in the next 3 to 5 years. And for utility, it depends. Can be viable today already. It depends on how many applications one can stack on one project.
I would say in our point of view, most of the projects we see have some tax benefit component. In the US, it would be mostly based on the ITC or investment tax credit, which we usually see for solar plus storage, where there's some regulations about a certain portion of the battery can comply for that. There's been talk of a larger scale storage specific nationwide tax incentive. Don't know if that will happen, but I'd say a lot of applications are very close to being able to stand on their own 2 legs, but we still see a lot of tax incentives at the larger transaction scale.
I know I moved the question off. I didn't want to cut anyone off, though. If anyone still wants to answer that question before we move on. Okay, well, so the next question is, what battery innovation impacts can we expect specifically for mini grids for energy access in off-grid and poor grid markets in developing countries?
I think the strategy is here to move to reduce the installation time, to get to really quickly installed system that are to a high degree pre-installed already, and to minimize the effort being done on site. So not in this case, I think the focus is not too much on a technology issue, but rather on reducing installation cost on site. And there I see a trend of moving more and more to pre-installed system, having the battery modules already installed in the container and not as a separate shipping, and yeah, going more and more to pre-installations.
Yeah, I would say the same. I think where we've seen solutions that are come packaged with solar, diesel, and batteries. One of the biggest innovations would be falling battery costs, meaning those installations, like we were talking about before, the diesel can be made a lot smaller. So you still probably can't eliminate it, but it can be made to operate less frequently and be operating more efficiently by charging the batteries, because the battery costs have fallen and these innovative package solutions have come on the market.
Andrew, do you think there's a case for second life batteries here as well? You know, we're going to have all these batteries at 80% state of health, perfectly usable, perhaps now just less energy dense. Is this a market that could use those?
Possibly. I mean, I think there's a trend to try to reduce costs that way, but I would say, you know, we also don't want to have the idea where, you know, we're sending our used batteries down to countries where they can't afford the new ones. I think where the new ones are falling in price, it'll make sense on a lifetime basis. And for most commercially financed projects that are going to be done on a large scale, which could really move the needle on energy access, nobody wants used batteries. It seems like if it's going to get financed, it usually wants to get financed with new batteries.
Makes sense.
You know, I find a lot of discussion about second life. It's a hot topic. Another challenge for it, though, is that the batteries are going to have worn slightly differently. So, you know, you need a good battery management system to deal with the fact that the batteries are no longer uniform. So there's challenges. Certainly going to be a lot of them, though, at some point.
Yeah, there's a lot of startups out there that are, you know, have technology to individually track the cells and try to resell them, but it's big challenges because, like you said, Peter, everything wears unevenly, and you got to know what you're buying.
And Peter, I just wanted to let you know we have about 3 minutes.
3 minutes. Well, is this the highest priority question, or, but it's the one at the top of the list. So non-electric alternatives to storage. This questioner mentioned biogas, but what about other things? Thermal storage, flywheels, chemical storage, hydrogen. What do people think about non-electric alternatives?
I would speculate that it's ammonia, hydrogen, but that's just speculation. I think there's a lot of development. I think when there's some new technology that can, as on the horizon, that will crack ammonia and use ammonia as a transport vector, and then into hydrogen, and then that's fuel cells. So I would guess that's the future, but speculation.
Yeah, we've seen a few hydrogen projects come along, definitely a small fraction of the projects we work on. But that, and I think another question down there was about compressed air, that we have seen some of those as well. So they seem to be rare and incentivized usually in some way, but that's not to say the cost couldn't come down. And I would agree with Michael that I think hydrogen is the most promising of the non-electric alternatives.
I really like biogas and biomass gasification, but they're a little bit like pumped hydro in the sense that they only tend to work well, work sustainably, and work economically in specific areas. So would love to see more of those on the grid. I think that those will complement whatever other energy storage technologies are on the market. Bring it on.
What we have found is that storing the product of the electricity, it can be extremely cost effective. In other words, typically it's about water pumping. You're storing the water and you're not trying to convert it back into electricity. And the same thing with thermal storage, I think has an enormous potential. It's not really comparable because you're not turning it back into electricity. It's more of a demand response, demand management. But it's still a form of storage, and it reduces the required size of the electric storage. So we think there's lots of potential for that.
In that sense, the question could be understood also about the potential of power to X technologies. I mean, as you said, transferring excess power to any kind of material, be it chemical process, be it water pumping or anything else, and I think that's actually a huge potential out there. Yeah. Not so much maybe on the technology development side, but more on the integration into processes, because the potential is there already. I mean, decreasing the temperature of cooling applications or heating up an aluminum shelter much more in order to make use of excess energy. I mean, the technology is there; it just needs to be used. The potential.
One of the flagship microgrids in the US is at the University of California, San Diego, and they've got this enormous tank for cold water, just so they chill the water off peak and then cool the buildings with the without the chillers during peak times. And it's a huge tank of cold water.
There are local heating grids in Germany that do the same thing. They take the heat from biogas plants, from the dairy industry, fed by the dairy industry, and they're able to feed that into a hot water loop for the local community. So the water is actually being pumped into your house and into your hydronic heating system, ideally a floor-based hydronic heating system versus in the walls. It's fantastic if you can get it.
Yeah, district heating and cooling is so much more popular in Europe. Although there are some university campuses and campus-like situations in the US, just not as in Europe, it's much more widespread. And that's, yeah, lots of potential there. Anyone else want to talk about more innovative storage concepts?
I might just say, I think always the thing to keep in mind with these novel storage technologies and approaches is, you know, while we can see a case for them in a increasingly high variable renewables grid circumstance, they won't be deployed until they have a market, right? And until grids are experiencing 75% renewable energy or something like that, all of these long duration energy storage concepts, while really interesting, just won't have a market. to deploy into. And until then, we'll just see more intermittent renewables and short duration storage. So like when we consider if we're going to be using these eventually, I think it's really interesting, but in the near term, it's very hard to find a place for these that actually makes sense.
Well, speaking as a flow battery manufacturer employee, it is our hope that the uptake of EVs hits the hockey stick and sucks all the lithium out of the stationary market so that there's room for vanadium flow and all these alternative storage technologies and stationary applications.
But I do think, Duncan, you made a good point that what's needed currently is not the same thing as that's what's needed for this vision people have of the 100% renewable future, or even the 90% renewable future. Those are two different things, yeah. So if there's any remaining last comments before I turn it back to Tricia? So Tricia, take it away.
All right, well, thank you all for that excellent discussion. Thank you, audience, for your questions. I would ask for the presenters can now turn off their webcams, and we will just share a few last minute details here. There are additional resources available for you on the conference website, microgridconference.com. You can look there for speaker bios and the sponsors virtual booths. After the conference, webinar recordings and PDFs of the presentations will be available to attendees. So watch for that link in our follow-up email after the full conference is over, which is today, but the email will come out next week. Thank you again to our platinum level conference sponsors, Rolls-Royce and ETAP, and to our session sponsor, Zant EOCycle. Be sure to visit sponsor booths at microgridconference.com and watch for the links. Thank you for joining us, and we will look forward to seeing you again soon. And this does conclude the 8th annual HOMER International Microgrid Conference.